So welcome back for the third lecture. I have various things to say, and I'll try to be reasonable. I'll mention some conjectures and a few open problems, and I'm not sure how much in detail I'll be able to talk about the basis exchange well, but as I went over last night, I realized it's rather ambitious. It would take about 2 hours to do justice, but at least I'll give a high-level indication of how that's done. But what I want to complete from yesterday is this implication. So just to recall, for the proverbial person that walked off the street, the entropy constant or the modified log-Sobolev inequality consists of bounding this entropy functional in terms of the Dirichlet form f log f, right, where I've written these two here. And P is a Markov transition matrix or Markov kernel with irreducible, and you don't need to assume reversibility, but most of the time we do. And it's reversible with respect to the stationary measure pi. And so I talked about the motivation being it captures decay and convergence to equilibrium in the sense of relative entropy of the distribution relative to pi. And then SUBGAUSSIAN concentration, which we have from the stronger log-Sobolev inequality, can also be derived with some additional assumption, sort of Lipschitz-type functions. And there are two proofs, as I mentioned yesterday. Let me find my remote. So my student, so first, just reminding people, going back one slide. So my W1 is the Kantorovich metric between mu and nu. These are the marginals, and you minimize overall joint distribution. The expected cost of sending mu to nu. The cost is, I'm assuming, is some metric, and in the case of a graph or a Markov chain, you look at the support of the Markov chain and you take that as the cost, the distance on the graph. And this is the dual, right? The dual involves maximizing or taking the supremum of E mu f minus E nu f over Lipschitz function, Lipschitz with constant. And again, recapping, I mentioned for SUBGAUSSIAN concentration, you might want to bound the log moment generating function of whatever random variable you're dealing with, right? So that involves establishing this. And the result of Bobkov-Goetze shows, right, from 99, that's equivalent to this entropy, this transport entropy inequality. Okay, square of Kantorovich. Again, this is a general form of Pinsker's inequality. So one way to derive, this implication from MLSI to SUBGAUSSIAN concentration is this, this work with my student Marcus Sammer. 05 was his thesis, and one thing for advisors and also to PhD students is if you don't have the student write up and submit to publication, it might result in 4 years chasing each other down from the thesis stage to publication. So under the hypothesis, so I mentioned this yesterday. Actually, is it too loud? No, it's okay. For me, it feels a bit. Right. So this inequality doesn't have any Markov kernel, right? Because you have these marginals and some metric and so on. And what I mentioned yesterday is that you can choose the best Markov chain you would like with invariant distribution pi, subject to this sort of a Lipschitz condition. That square of the distance times Lxy, where L is minus L is the usual Laplace. Right? So that's sort of the flexibility you have. And we followed this proof of Otto, Felix Otto and Cedric Villani, where they showed log Sobolev implies a stronger W2 transport entropy inequality. And so you start with, right. So you let nu t evolve according to your Markov kernel, okay, and let ft be the density. Now G sub t is a solution to the dual problem. So sometimes the primal is called Monge and the dual called Kantorovich problem. So I showed you the dual formulation, supremum over all Lipschitz f, e mu f minus e nu f. It's that f. Okay, this G sub t is that dual. And as I mentioned yesterday, you look at the two derivatives, the derivative of Vassar's time derivative. Okay, formally, you can show that that's at least the Dirichlet form. It's the from above, yeah. Because we're going to show that at t infinity, we know how these the two things we want to relate are. At t infinity, both are zero, they're equal. Which both this transport made, because nu t, since it's evolving according to pt, is going to be pi as t goes to infinity. Okay, and similarly, relative entropy, which is what is on the other side of, right? So these two, so the point is this is going to be nu t. So at t equals infinity, this is equal to pi, this is equal to pi, so both are zero. And we're going to show by looking at the derivative from the right and establishing an inequality, they must be equal at infinity. So and then if you show that one has a strong, one dominates the other in the growth, then at time equals zero, the one that dominates in growth must have started below. So at t equals zero is what we are interested in. That's sort of the logic. Okay, so your measure of interest nu is going to be at nu p0, at time zero. Yeah, so the point is you bound this from below by the Dirichlet, and then you do this calculus inequality we did a while ago. Y related to ft log ft, because this is what MLSI gives us, right? Modified log Sobolev gives us a way to relate this Dirichlet form to relative entropy. So that's the, and then for this calculus, that's where you're going to use the Lipschitz property of GT, and then this is the one that I showed the proof of in lecture 1 that compares log Sobolev to modified log Sobolev, and the hypothesis on the kernel. Okay, so these are the ingredients. And again, I flashed this briefly towards the end of yesterday's lecture. This is showing that, how much we want to show at time equals 0, this is larger than that guy. And so in the growth, it's the other way around, and at t equals infinity. Okay, so that's the, all right. So again, this is a reminder that while we know Gaussian or sub-Gaussian tails follow from log Sobolev, our issue is for lots of examples, this is typically smaller order than alpha, than modified log Sobolev. That's why we're bothering to go through this exercise that people knew how to do starting from log Sobolev. So this is, so this is a similar implication of what I just went through, okay, under an assumption on alpha, the modified log Sobolev. You want to derive sub-Gaussian. And my assumption of summation d square L is replaced by this type of condition without any other assumption on f. So if you say f is Lipschitz, then this is basically what I had. Yeah, so this is usually called the Herbst argument. And so we want to establish, as before, a bound on the moment generated function. So this conclusion follows. And It's basically a 2-slide proof how to do that. Okay, so again, we want to establish this for appropriate C. So you start with this. So basically taking the right-hand side to the left-hand side, e to the ct squared. Look at ft of x, where C, as I said, is no longer secret because that was the term that had these things. Alpha, modified log Sobolev, and the quadratic variation bound. Yeah, so one slide is to write the Dirichlet form and use the hypothesis to bring in this new effect. So let's just go quickly. So by definition, I have the Dirichlet form definition here. So pi x pxy ftx, and then log ft, log capital Ft minus log capital Ft becomes, because the capital Ft is this, the ct square cancels in the subtraction, and you have t, so the t comes out here, okay? It's just substitution of ft of x in this definition of Dirichlet. And this is, again, an equality, just taking out a factor of ft of x. And now you use the hypothesis that defined this mu of f. Okay, so what did I do here? Yeah, so okay, here we did this standard inequality so that you end up with the quadratic variation. That's slide 1. And the second slide is now, this is again a little bit like the previous proof by looking at the derivative. So this is a fundamental theorem of calculus at some level. So now you look at the entropy of Ft. We looked at Dirichlet form of Ft log Ft. Now we're looking at entropy of Ft because we know the two are bounded by alpha of P. Right? So entropy of Ft is 1 over alpha of P times Dirichlet form Ft log Ft. So that's replaced by this from the previous slide. And then some computation shows what happens to the derivative. Yeah, so again, I think I was too lazy and just taking the limit appropriately from above, below, but without bothering. Okay, so maybe let me move on. The point is to say this is a standard argument that somehow people, including Borkar and I, missed in having a clean conclusion without assuming anything about the function f except for this quadratic variation. So it's a nice conclusion by Jonathan Herman and Justin Sales. Okay, now, so the next few slides, what I want to address is, so, I spent quite a bit of time showing, okay, computing this on some examples, right? The symmetry grouped transpositions and some other small examples. And these are some conclusions. What's a big problem is how to establish a modified log Sobolev inequality. Besides directly computing it, when on problems that have a lot of structure, are there sufficient criteria, right? What sort of things? Again, it's not particularly rosy. So in the matroid basis exchange case, there was sort of a nice geometry/algebra that helps, as it turns out. The notion of strong log concavity of the generating polynomial of the distribution that you're interested in, and so on. And there's another sort of a second, let me say, there's a local, I'll explain what I mean. Second derivative condition, known as Bakry-Emery criterion. So second derivative, because we already saw this was inspired by taking the time derivative of entropy. Time derivative of entropy is equal to minus Dirichlet form, and that's what gave us the definition of alpha. So you can take the second derivative. That's the point. So first, so besides Bakry-Emery, I have Bochner. So I think this is attributed to Bochner and then later Lichnerovitz. So before showing you that Bochner-Bakry-Emery, I want to show you something similar that was done for spectral gap, for the Poincare inequality. Okay, what happens when you take the second derivative compared to the first derivative? This is again fundamental theorem of calculus. So we know lambda, right, spectral gap that Fabio started his lecture with, and I also discussed, is this Dirichlet form, symmetric one, FF divided by variance. This proposition is saying that's equal to something else. That something else I'm going to call mu, which is terrible notation. I apologize. I'm using pi for measure, mu for some function or constant. But this is what we had in a little monograph I wrote with Ravi Montenegro. Okay, so no, indeed, the first derivative is here and then variance, right? D over dt of variance of ft, if you have ft, that's the density of the chain at time t, will give us EFT of t. Now that's in the denominator, and what is this? Okay, so this is a second derivative term, turns out. So this observation or proposition says these two are equal. And there have been cases where this was used. Somehow, I haven't seen, at least in a sort of community Markov chains and so on, a way of using this. Okay, but there are some papers where that turns out to be handy. They're equivalent, so it cannot be like super useful somehow. Sometimes that formulation may be nicer. Okay, so let's see the proof. So one direction is Cauchy-Schwarz, as I indicated here. So assume mean is 0. And the definition of the Dirichlet form is this, in a product Fn minus Lf. By Cauchy-Schwarz, you get that, and then replace this by, okay? And if you square these two sides, then you get the conclusion. So let's see the other side, which is, as I said, second derivative and integration. So neither side is particularly difficult. So it's probably maybe more surprising that it's useful. So we have the first derivative, that's the Dirichlet form. Now take the derivative of that, you get the term that we're dealing with. So HT, by the way, is this PT applied to F, HT for a heat kernel order, okay? Where P sub T is e to the TL, L is the Laplace, yes? Okay, so this, I might have called it P sub T before. So we know this HTF or F sub T goes to the average of F as T goes to infinity. And so the Dirichlet form is 0. So as I said, just write the Dirichlet form because this guy is the derivative of that, time derivative, by definition. And, oh yeah, here I tried to be careful and not use reversibility. So technically, there's an L star here. So what is L star? So if L is reversible, then it's self-adjoint. But otherwise, you have to, when you move L from the right to the left, you have to take it to L star. And L star is, so if P is not necessarily reversible, then P star is the time reversal of P, which is so if P is reversible, we have this for all xy. If it's not, then define P star to be so that this is satisfied. And L star is just P star minus. But so lambda P, turns out to be lambda P star. There's something I mentioned in the first lecture, that somehow this formulation for EFF automatically symmetrizes it. Okay, so switching that doesn't make a difference because, in a sense, we're proving that lambda P is at least mu P star, but lambda P, which means lambda P star, is at least mu P. But so that's sort of a little technical. All right, so this is, you have a nice equality. The point here, to take away is you have a nice equality in terms of the second derivative with respect to first derivative. Okay. What happens if you try to do this for the entropy constant? So that's what Bakry and Emery did in '85. Here it turns out it's not equivalent, but at least it gives us the good direction in the sense it gives me something that implies MLSI, as I indicated on the board. Okay? So if you bound this quantity, now again, just as before, the denominator is the first derivative of entropy, and the numerator is the second derivative, which has two things, and this causes a headache, as in, because it turns out you can control one, but the other one is problematic in application. There are papers by Pietro Caputo, Fabio's colleague, and collaborators, Paolo Daipra and Gustavo Posta and Boudou, that have used this for some birth-death chains and some other interacting particle examples. This formulation, because if you manage to bound this, and for spin systems and birth and death chains, you can control the rate somehow. You can define the rates so that you make these, the contribution of these terms. If one of them gives negative terms, you can compensate for it with other positive terms and so on. So there's some flexibility with this formulation. Okay, so in any case, the other reason I want to mention this is, so notice that both these formulations, the second derivative criterion, so this is not local actually, because we are still averaging over the measure pi, right? There's this Dirichlet form EF log F everywhere, numerator, denominator, okay? In the spectral gap case, it's equivalent. In the modified log Sobolev, it's, it turns out it's stronger. But by local, what I mean is there are now papers on this discrete curvature, and also in the continuous case, they correspond to the so-called Ricci curvature, which make a stronger assumption, or which demand something stronger, and the something stronger is that you control these two not on average, but point-wise, without averaging over pi. Okay? For every f, for every x, or for every xy, you want the inequality. Of course, that's stronger than saying once I average over the distribution pi. So that's what I mean by local here. So there's a local second derivative type criterion. As you can imagine, that gives you a lot more power if you can bound that. So it's somehow a strong form of convexity, asking for something like that in a local way. But people manage to do that, and in a paper that used that sort of a notion as a discrete curvature with Matthias Sarbar and Jan Mas, we used that formulation to rederive the bounds I had mentioned to you in lecture 1 for the slice, k-slice of the discrete n cube and random transpositions. Unfortunately, while we could get the good bound for the k-slice, we can only get a bound of lower bound of 1 over n square for random transposition. And I showed you proof of 1 over n, order 1 over n. Okay? So we can bound this stronger local second derivative criterion, which implies modified log Sobolev. But we already know modified log Sobolev is order 1 over n. We can only prove 1 over n squared using this. We don't know if something stronger is not true. We just can't establish. So we left that as an open problem. Right? We get the tight bound for the first one. The k-slice is called also Bernoulli Laplace diffusion and so on. But it's just, in our context, it's the state space is the n choose k binary vectors of k1s with the replacing one and swapping ones and zeros as the dynamics. Okay, so this is alluding to that. So let me segue a little bit into this second derivative criterion. So there's also a local second derivative criterion for lambda. If you average, we just saw proof that that's the same as lambda, right? But you can ask, what happens if you strip away the expectations and ask for something local? Okay, so there's a notion of curvature based on that. And, people derive various inequalities. But in this discrete curvature, there's only one result that I'm aware of so far that I find satisfying. Not just because somehow I'm involved in that work, but there are two other proofs of that, actually. The reason I like that, it gives you a curvature-free statement at the end. You use this rigmarole to derive something, and the something is that the classical Cheeger inequality is tight for random walks and Cayley graphs that come from abelian groups. Okay, so given any group, you can define a Cayley graph, basically using the generators of the group to define the adjacency. Right? The elements of the group are vertices, and then the generators tell you what the edges are. And we have a theorem that says if it is abelian, it's the group, and it turns out the abelianness is needed, then the spectral gap of that random walk is at most square of the Cheeger constant. Usually, it's always at least square. What we derive is that it's at most square of Cheeger up to a factor that's the maximum degree of the graph. Okay, so in terms of the dependence of Cheeger, it's the quadratic. In general, spectral gap is at least square of Cheeger and at most linear in Cheeger constant. But we show that the square is actually tight by deriving that. And we prove that by showing, so I'll have slides I'll show, but before we get lost in technical stuff, I wanted to say what it's about. We prove that in two steps. We show for any Markov chain that has non-negative curvature in this sense of local Bochner criterion, you have such an upper bound. That spectral gap is at most quadratic in Cheeger. And the second result is that for abelian Cayley or Cayley graphs coming from abelian groups, you have non-negative curvature. So the conclusion is curvature-free in the end because of that. For a class of Markov chain, you can identify. So the more general question of what are the class of reversible Markov chains for which spectral gap is actually up to a constant or constant depending on the degree, quadratic in Cheeger, that's open. But at least we identified a fairly general class of Markov chains. Yeah, I am not as familiar with that literature, but Laurent Soloff-Cost and also people in differential geometry, they have a bunch of papers that, and they also look at these Nash inequalities, Harnack inequalities, and so on. Yeah, it's quite a bit, but yeah. Okay, so since I already mentioned what this is about, I will, so again, another name I should throw in is Schmuckenschlager. He actually used this notion of the second derivative criterion to introduce, to suggest that this is perhaps a notion of Ricci curvature for Markov chains. But it didn't get developed while he introduced it about 20 years ago. Okay, so the formal definition is something like this. So what are these Greek symbols? So gamma FF is our usual Dirichlet form, except strip away the outer summation and pi of x, because it's local. So this is basically f of x minus f of y times f of x minus f of y, sum over all y, pxy, without the averaging. Delta is the usual Laplacian here. Okay, here, so I apologize, this is for the graph version. So rather than p minus I or I minus p, I have D, which is diagonal of degrees of the graph. A is 0, 1 matrix of adjacency. Okay, so if you divided delta by the corresponding degree, that's like before. So this inequality is essentially saying locally a second derivative term is at least some k or kappa times local first derivative term. If that's the case, then you say it has curvature. And you can say, okay, what good is this definition? Can you tell me what it is in example 1, 2, 3, 4? Okay, we'll show. It turns out it's not so bad to compute. I'll show you a couple of slides that give the details. So again, to write it down explicitly, the Laplacian is this, right? If you, rather than the graph case, you want Markov chain, you would say over all y such that summation f of y minus f of x times pxy. That's the only difference. Here it's a 0, 1 kernel. And as I said, gamma of g is this, see, without the pi of x and so on. You can also view it, gamma of f, as gradient of f squared, the discrete gradient. So this is called by Felix Otto and people that tried to discretize some of his work for Markov chains, gamma 2 calculus, taking this second, and gamma 2 of fg, you can define somehow using the usual rules that go back and forth between gradient, Laplacian, and divergence in calculus. This is doing it in discrete. So it gives you a certain definition of gamma 2 in terms of gamma 1 or gamma and delta. And so you say, the previous definition is the same as saying compactly gamma 2 locally for every f, every x is at least some constant times gamma f. So it's a very strong criterion. But the advantage is you can verify it locally for graphs with symmetry. And that's why Cayley graphs are nice, right? Because it has some group structure. It's easy to, you don't have funny, strange behavior here and there. If you have an arbitrary graph, there are no guarantees. Okay, so again, this is just to say, in terms of computations, you need to open these up. Yeah? You can move symbols around only for so long. To work with them, you actually have to write everything explicitly. And this, the point is to say you can write everything down explicitly. And the other point is to say, when you're trying to deal with Dirichlet form or the gamma function, you just worry about the neighbors. What we're trying to do with the second derivative criterion, local or global, is look at the second neighborhood, right? To capture convexity, you want to see how much the function is changing 2 steps compared to 1 step. That's sort of the high-level idea of this. And so that's why you see v adjacent to x, and u adjacent to v, v adjacent to x, and so on. Then, so this is work with Boaz Klatta, Gadi Kozma, and then my student Peter Raleigh. I was going to say, once you have something like this, you find a grad student and tie them to a chair and say, please compute. In my case, I was lucky. Peter Raleigh actually is happy to be locked up in a room and in a chair to do this kind of math, so I'm blessed. And so he, for example, he computed various standard example. These are for graphs, that's why these look like some integer values, but for Markov chains, you basically divide these by the transition probabilities. Okay, for a symmetric group, you get like order 1 over n squared. And we also found in the literature an example that where you did not have the abelianness, and then Diaconis Salov-Kost computed spectral gap and the Cheever constant, and indeed it doesn't satisfy. So if I look at the spectral gap order 1 over n cubed, it's not bounded from above by square of Cheever. That would have been 1 over n to the 4. Okay, there's an example. Again, as I mentioned, our result, so for graphs, this is how it looks. For Markov chains, you remove max degree from here and you put on the right-hand side, basically. Okay, either way, we capture that. So this is in general. What we capture is that lambda is at most quadratic. Okay. And it's done by, the curvature assumption gives us a certain isoperimetric inequality. And then if you plug in the curvature is non-negative, it gives you what you want. And the third thing that we need to verify is that abelian Cayley satisfy the curvature property with none. Okay, so that's sort of. So we don't have somehow as nice conclusions if you talk about modified log-Sobolev. All this stuff is to show that at least the local second derivative criterion you can work with and derive interesting consequences. So this is still an area that our people in probability are also working. Max Fati, Matthias Urba, the PDE people are also interested. So some open questions here. Can we characterize those that satisfy non-negative curvature, right, beyond abelian Cayley? A more general question, when is Cheeger tight? And so again, maybe in the open problems, tomorrow I'll mention this very interesting lattice non-crossing partition. This is again this Catalan object, but it comes up in free probability, and we don't understand many things about it. So there's a, continuing the theme of this curvature, discrete curvature, there's yet another notion that was again in my student Marcus Sammer thesis, the one that did the derivation that MLSI implies sub-Gaussian. It was in the last chapter of his thesis. He was wrapping up, ready to go, so I didn't encourage him to develop it further. And I didn't think it was particularly novel. It was basically like a Dobrushin criterion to define curvature. But a year or two later, Jan Olivier developed it significantly. And so it's now known as Olivier curvature. It's probably, we could say, Dobrushin's notion, the way I said Bochner curvature. What is it? So back to our Kantorovich metric W1, okay? So given any finite Markov chain, locally you say this coarse Ricci or coarse curvature is kappa xy if, when you take x and y, which are, say, neighbors in the sense of Markov chain, look at what happens after one-step evolution. So then you have, I'm calling them mu x, mu y, okay, where the Markov chain takes x2. Look at the best way to couple them. In other words, the W1 Kantorovich metric between the two. If you can show there's a contraction, because at time 0, you took x and y that are at distance dxy, let's say point masses. So dxy could be neighbors, and you might want to call it 1. But the distance is up to you. For adjacent pairs, you define distance any way you want, and then use the usual graph distance, the graph of the Markov chain support. So this coarse Ricci or Olivier curvature Ricci notion says for a pair xy locally, curvature is kappa if you can show W1 is this. Inequality is fine if you can show W1 is at most 1. Then you say, suppose you show W1 is at most this, then you say kappa xy is at least whatever you have. It's easy to do, these computations and show for the discrete cube, the curvature is order 1 over n. And for symmetric group, the example that I spent some time on for transposition is order 1 over n squared, and so on. Because W1 is easy to, this is, in computer science, it's also called path coupling, right? Trying to couple two that are nearest neighbor. Okay. So this is a short proof as to why this is order 1 over n. Let me move on. Similarly, there's a short proof, sort of most natural coupling for transpositions on cards and n cards, the n factorial will give you order 1 over n squared. Okay, to show, once you find something that you think is a good coupling and a good bound on curvature, again, the dual formulation of W1 is often useful to show that, in fact, one could not have done better to show your coupling is. Okay, so what I wanted to mention is the reason I showed you this coarse Ricci is somehow there's, so Yuval Perez asked this question, if you have a lower bound of kappa in the sense of the coarse Ricci, meaning suppose using path coupling, you could show curvature is at least some kappa. Could it be that the log-Sobolev constant is at least kappa of the market? So I said, I doubted that, and I said, well, I would aim for something weaker. Modified log-Sobolev constant maybe is at least kappa. So that got turned into Ronan Aldan, James Lee, and others calling it a conjecture by the two of us. And I think at least one of us will be happy, no matter which way it will be settled, because I'm not sure I believe the conjecture. So, but again, the question is, if you show that in the sense of Olivier, etc., the curvature is kappa positive, then does it imply? Okay. This is again, we are asking for something upstairs that implies modified log-Sobolev. While we don't know, there's a short paper by Eldan, Lehak, and Lee that shows something weaker. Yes, Fabio. Yeah, something strictly less than 1. Because kappa. Oh, I should mention, thank you. It's classical, and I think at some point Yuval and I chased the literature down, and Percy pointed us in the right direction. A paper of Mufa Chen that shows if you have this, then indeed spectral gap is at least kappa. This you know. If you show path coupling, gives you contraction by 1 minus kappa, and spectral gap is at least kappa. This is classical, this is not. Basically, you can define an eigenvector, proxy to an eigenvector that gives you a bound. So it's natural to ask, can we derive something stronger? Namely the entropy constant. Okay? So this is not known, and since I mentioned to you that MLSI implies sub-Gaussian concentration, what these guys said was, well, let's try to prove something even weaker, and indeed they managed. Okay, so at least if you have the contraction by path coupling, you have the sub-Gaussian. And there's work of Catalin Martin that's actually similar to what these guys did, but I forget the dates sometime on. All right. So any questions on this stuff? Lots of open problems, but no. There's a few more, I'll mention later. Okay, so recap from yesterday of matroid. I'll try to go quickly. Right, we have these axioms that define what are independent sets of a matroid, and then the largest independent sets are bases, and you can go from one to any other basis by exchange of ground elements. And R is used to denote the rank and so on. And the basis exchange walk is remove any element uniformly. And so in this version of the basis exchange, as I said yesterday, you remove uniformly. So if you have R is the rank, so if you have R elements with 1 over R probability, you remove one of them. But then in terms of replacement, you put in with probability proportional to how many will give you a valid basis. So you're looking at near basis. Total number of elements may be n, but how many of those are, when you add to the near basis, give you back a basis? If it's k, then with probability 1 over k you go. Okay? This is a more general setup I'll explain in the next few slides. Turns out if pi is uniform, that's what you get, but pi can be a more general distribution, so-called homogeneous, strongly log-concave. I'll say what that is in a second. So this step, that's what's new. People mostly studied uniform addition and removal, but the addition non-uniform is what's interesting in this. And the theorem I mentioned yesterday is that then the modified log Sobolev constant is at least 1 over R. Actually, as I will indicate in the proof, they show this entropy decay by basically 1 minus 1 over R. They don't need the modifier. This is something I pointed to Heng Guo, who explained the proof to me. So you can they directly analyze the entropy decay of this Markov chain. But then, they soup it up and then they put it in the language of an actual modified log Sobolev inequality because of consequences such as SUBGAUSSIAN concentration and so on. Okay? If you're interested, if you care only about the mixing time of the Markov chain, the proof doesn't have to go through this. Okay, so this, I put this here rather than at the end in case of time issues, but let me at least state some of the jargon I mentioned. So here is the algebra / algebraic geometry. Okay, so I mentioned homogeneous, strongly log-concave. So I'm trying to get to the definition of that, which tells you what's the general class of probability distributions on the basis of a matroid that you can sample from. Okay. So polynomial with non-negative real coefficients in X1 is log-concave. So this is standard. Log-concave if the log has the Hessian that's negative semi-real, right? So Nabla square log of the polynomial is negative semi-real. So it turns out that implies, and again there's some reverse direction also, but for what we want, this is a useful direction. Turns out a particularly useful condition, and this is crucial to all these results on mixing, the spectral gap and entropy contraction. Then that implies the Hessian has at most one positive eigenvalue. At most one positive, and typically you understand what it, and the others are all negative. And that gives you the way they reduce the problem to some two-level problem, spectral gap immediately. Okay, so that's, yes, yeah. Look at this. And now what is strongly log-concave? So you say strongly log-concave if for any subset of the indices, these partials are also log-concave when you evaluate at the all ones. So again, you're mostly interested in the positive ortho, but this is for, you take singletons. So if you take the full thing that gives you the log-concave, but now you're saying for all these partial. This has at least 3 different names now. So Leonid Gurvitz introduced it 10 years ago. I think he called it strongly log-concave. And then the recent work, Nima Anari, Oves Garan, Cynthia Vincent, they call it completely log-concave. And then even more recent, they call Lorentzian polynomials. So, but the notion is all the same. Now, when do you say a distribution is strongly log-concave? Because I said pi, like pi, the distribution on the basis of a matroid would be strongly log-concave. Or you say the distribution is strongly log-concave if it's generating polynomials. So the distribution over subsets of your underlying ground elements are the coefficients, and then you have this is the generating polynomial, right? So these are the variables. And so the point is, the relevance is that a nice general class of such distribution is in fact when the support is over the basis of a, say if it's a uniform distribution over basis of entropy. And this nice recent work of Peter Brandon and Juneja showed that in fact it's equivalent. So it's nice but also disappointing in the sense that the best things that you can do with this are actually the matroid basis, because the characterization is that an R homogeneous, so it's a multivariate, and the degree is at most 1 in each variable. R homogeneous multi-affine with non-negative coefficients, strongly log-concave, if and only if the support of it is the basis of some matroid. And after taking, the second one is also beautiful, and it's very useful. After reducing it to a quadratic, it's real stable or degenerate. Meaning so it's of degree R if the rank is R, right, for matroid. After taking R minus 2 partial, quadratic is real. So real stability was first explored quite a bit since particularly the work of Marcus, Srivastava, and Spielman. Sorry? Yeah, no, it's fine. So it doesn't vanish above the upper half. Okay, this is the imaginary. Yeah, so real stability, and then the strongly relative, all this was explored first, but now this is a nicer class that encompasses that. So the motivation came from trying to find something larger, in part because so real stability at least helped in understanding these balanced matroids and at least some of those, but then they knew there was more because it didn't give all the matroid. So basically, the notion of balanced matroid that deals with negative correlation. If an edge is in the random spanning tree, probability that another edge is also there is negatively correlated. Is at most the unconditional. Such things, but this goes the full. So again, now, okay, hopefully homogeneous SLC pi part makes sense. Okay, now we're talking. But this is just saying we're restricting to polynomials that are homogeneous because homogeneous polynomial. Yeah. So because all bases have the same side, right? Like the only on basis, exactly. However, good. I'm glad you mentioned the word independent sets because we're going to look at that in a minute. Okay, so the point is immediately implies this nice bound. So first, these people, also with Liu, obtained spectral gap, and so R times log of the number of bases type bound, and then that got pushed to R times log, as I explained, because of entropy decay. But independent sets play a crucial role. So this is something else that all the previous attempts had missed. I mean, people thought of, because of the success of analyzing Markov chains on perfect matchings, also using near perfect matchings. We tried to, but in a more elementary and naive way, look at bases and near bases and look at some attempted proofs of mixing. But in this work, it turns out the secret to solving the problem at the level of basis, secret or hardness, goes by looking at the entire ladder, independent sets all the way up to the empty or singletons. There's a recursive bound you can get, and then the R minus 2 derivatives and the quadratic polynomial you get being real stable is a hint that our task is somehow reduced to doing something at the ground level. Okay, independent sets of size 1 and 2. Turns out that's the base case, and then by induction everything follows. That's sort of the 30,000 feet view of, of what they've done, which is, of course, to do the whole proof, it would take an hour. But it's all developed nicely, beautifully. So you start at the top, right? Somebody annoying like me gives you the distribution for the basis. I defined on independence of rank R. And you can define the corresponding weights all the way down. How? So if I has cardinality R, then that's pi, that's given to us. That is this strongly log-concave, blah, blah. Now for other ones, you define by saying, look at all the guys that are cardinality 1 above and add up their weights. You define the weights, but then you're always normalizing, so at each level you have a distribution, probability distribution. At the top level, you have pi sub r minus 1, dot, dot, dot. Okay? So z's are normalizing constant. That's why at the top level, z sub r is number of bases if the weights are 1. Okay? So that's kind of the stratification of this. And there's a little dictionary. So there's these 3 colors, if you can tell, black, green, and red. The way I'm not good at creating tables, so this is really terrible. But what I'm trying to convey here, as Heng Guo explained to me, polynomial, at the polynomial level, so I'll wrap up in just 2 minutes. Taking a partial with respect to variable xi is equivalent to setting that variable xi equals 0 in the, sorry, I just violated. I should go black, black, black. Is equivalent to contraction of that element. Contraction means you take an independent set, or start with basis. So you pick your favorite element. All bases that contain that element correspond to basis of another matroid called the contraction matroid. Basically, you take that one for granted. Okay? So taking the derivative is like taking that element for granted. In terms of probability distribution, it's like condition on having I. So you assume that you always have I. Similarly, setting a variable to 0 corresponds to deletion. This is also a deletion matroid. All bases that don't contain a given element corresponds to the deletion matroid of the original. That's probabilistically conditioning on not having that. Okay? Similar. So there's this translation. This is what the polynomials, the algebra of polynomials is giving us in terms of probability distributions over independent set. Turns out these strongly log-concave ones behave nicely because it percolates all the way down to something we have to check at level 2. And so they define this down, the analysis is done by looking at down, up, and up, down, but let's just focus on down, up, which means I'm at level k, size k independent sets. I remove uniformly one element, but I add an element with probability proportional to these weights. These P's are these projections, as we'll see here. Yeah, so pk plus 1 down means with probability 1 over k plus 1, I go down to the kth level from having independences of size k plus 1. Up goes not uniformly with 1 over k, but with these weights, right? With how many guys of weight k plus 1 are containing this weight k1. That's why it's this divided. Okay. So the analysis is facilitated by looking at the basis exchange walk in this down up or up down using these projection matrices. And so the key, to conclude key lemma, what it says is pk down for any k contracts relative entropy by 1 minus 1 over k. So when you go from k, level k to k minus 1, you look at a function at the level k, look at what happens to projection 1 level, it contracts. And that's proved by induction, and the base case, as I said, is the 1 and 2 level. And there you can do the computation sort of precisely. And if you say, well, where is all this strong log concavity, etc., coming from? Turns out what you have to bound in terms of comparing the entropy contraction at the bottom level turns out to be something non-negative because there the top eigenvalue is positive, all the rest are all negative. And so something like this that you have to show non-negative follows because of the knowledge of the eigenvalues of that strongly log-concave polynomial. Right? The Brandon type result that said it's strongly log-concave implies and is implied by the stability at the ground level. So that's sort of, and then the relative entropy decay is sort of easy, Jansons, etc. Okay, let me stop there. Sorry, I went over. Yeah, but so I mentioned half a dozen names: Juneja, Peter Brandon, Anari, Cynthia Vincent. Have any of those people come, but make sure they give you 2 to 3 hours. Otherwise, it'll be this flashy proof. No, because first you need a lecture on log concavity, strongly log concavity, and then a little more refresher on matroids and basis exchange, and how the things really fit nicely together.